Okay, let's get started, please. So there are a couple results in this chapter that I was going to skip over, but I realized that how could I skip over this theorem, which is due to Abel? He missed it. Yeah. Okay, so which says that if you have summation A sub n, summation B sub n, which are convergent series, and C sub n, summation C sub n, the Cauchy product, then if C sub n, if the Cauchy product converges, then it converges to summation A sub n. Okay, so if it converges at all, it converges to the right thing. Okay, and I wasn't even going to mention this theorem because I'm not going to prove it. I was just going to state it, but you could read it in the book. But I thought, how could I skip over this theorem in this class in particular? Okay. Okay. So yeah, I think I'm not going to talk about rearrangements. If you want to read about rearrangements of series, just do it yourself. The main thing is that the main two results about rearrangements are that one, if your series converges but not absolutely. We mentioned this last time, right? If your series converges, but the series doesn't converge absolutely, then you can actually rearrange your series to converge to whatever number you feel like. Then you can, So this is basically, you're wondering, you're in elementary school, and you look at sums of numbers, and you notice that if you change the order of the sum, you still get the same number, right? Like 1 plus 2 plus 3, 3 plus 2 plus 1, you get the same number. Okay, so you'd think that the same thing would still hold. You might think that the same thing might hold for series. It's very, very false. Okay, if the series converges but not absolutely, then you can rearrange your series to converge to whatever number you want. I could make my series converge to 0, to 10, to pi, to whatever you feel like. You can rearrange it to whatever you feel like. Okay. On the other hand, if it converges absolutely, then all the rearrangements will converge to the same thing. Okay. So all rearrangements to the same limit. Okay, and I'd like you to read that result. Don't read the first result, which is long and complicated and sort of not worth it. The second result is short and simple, and you can let you read it by yourselves. Okay, so okay. So we are entering now into basically the last section of the course. So as I said at the beginning, we will jump into chapter 7, which is sequences and series of functions. Sequences and series of functions. Okay. So I may do a little bit about chapter 6, which is about integration. But the thing is that chapter 6 is about something called the Riemann-Stieltjes integral. And basically in math, you throw out that integral in a year or two anyway, and replace it with something called the Lebesgue integral. So I sort of feel like what's the point of introducing all this stuff when you're actually going to get rid of it in it? When you take your course in measure theory or 137, then you'll learn the real integral that people use. So anyway, and further, the stuff in chapter 7 is very, very important. So I'd like to get to that. Okay. So sequences and series of functions. So, right, up until this point, we've been talking about sequences of points in a metric space, right? You've got these points in a metric space, but now we're going to think, each of those points is a function, okay? Each of those points is a function now, okay? We're going to talk about what does it mean for these functions to converge to another function, okay? And there'll be different ways that we'll think about convergence, like, and some are better than others. Okay, so we'll start off with our first kind of convergence, which is the one that won't work so well. Okay, so the first kind of convergence is called pointwise convergence. Pointwise convergence. Okay, so here's the definition. So you have a subset of X, a metric space. Okay, so you have some subset in a metric space. You have a sequence of functions, complex value functions, defined on that set. Okay, so you have these f sub n. Each of them is a function on. Each of them is a complex value function on E. Okay. Okay. If for each point in E, the limit of f n x as n goes to infinity exists, call it f of x. Call that value the limit f of x. Then we say that the sequence f sub n converges pointwise to f. Okay, f is the pointwise limit of the f sub n's. Okay, so let me make this concrete. F sub n. Let f sub n x be x to the n. Okay, suppose we are on 0, 1. We're on the interval 0, 1. Okay, and we're looking at the functions x to the n. Okay, so here we are. Here's 0, 1. Right. The first guy is going to be x to the 1. The second guy. Right, the second guy is going to be x squared. The third guy is going to be x cubed. Right, the fourth guy is x to the 4th, and so on and so forth. Okay. Now, if I choose an arbitrary point x in my set, I look at the limit of fn x as n goes to infinity. What happens? What do I get? Well, suppose I'm at 1. So this is my x is 1. Well, fn of x is always going to be too easy? Too easy? Yep. 1, right? It's always going to be 1, right? So, let me draw my f down here. My function is going to be 1, right? At 1, max.
Sorry.
Okay. And what about if my function, what about my x is anything other than 1? Well, the limit's going to be right. If I have, so I'm looking at my function, right? My function, remember, is x to the n. So the limit of x to the n is x as n goes to infinity, right? And my value is between 0 and 1. What are you going to get? So you're going to get 0, right? Right. So my limit function looks like this, right? This is my limit function, right? This function is the pointwise limit of these functions. Okay, this is when you want to think. Okay, so at each point, as you let n goes to infinity, you end up here, right? Okay. Okay. Everybody okay? Any questions so far? Confusing? Not confusing?
I don't understand
where it collapses onto the x-axis. Yeah.
Well, suppose I take a half, okay, and I look at fn of a half as n goes to infinity, right? So fn of a half is 1/2 to the n, right? As n goes to infinity, I go to 0, right? So if I take 3/4, well, I'll also go to 0, right? If I take any number less than 1, it'll go to 0 as n goes to infinity. Right? Okay, so this is what's called a pointwise limit. Okay, so that was an example. Let me give another example. So we're going to define another set of functions on 0, 1 in a funny way. Okay, so it'll be like this. So F1 is going to look like this. So F1 is going to be this constant function. So at the height of 1. Okay, F1 is this guy. Okay, F2 is going to be this guy. So it goes from 0 to a half. Okay, but it has a height of 1, and then it's 0, 0 elsewhere. Okay, F3 is going to be this guy. It starts from the place that F2 left off. Okay, it starts from the place that F2 left off, that is to say a half, and it gives you, it has a length of 1/3. Okay, so this length here is 1/3, right? Where F2's had a, so when I was introduced to these way back when, the professor called these blimp functions. Okay, so you got this blimp, right? The first one is length 1, the second one is length 1/2, the third one is length 1/3, and so on and so forth. Okay, and the blimp, you know, keeps on, right? I keep on adding on to where the blimp keeps on adding on to where the last guy was. Starts where the last guy ended, and there's a wraparound effect. Okay, so right when you get to 1, it comes back from the left-hand side. It's like a video game. Okay, so this blimp goes bloop, 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 and it starts shrinking. Okay, the blimp starts shrinking in size. Okay, so does these things, what happens to fnx as n goes to infinity? Okay, so yeah, so what happens, pick some point x, and what happens as n goes to infinity? Okay, talk with a neighbor. I feel like you guys should sit like in the group. Why are you sitting on the side? You don't like everybody? Sit in the. It's up to you. It's up to you. Maybe that's better.
It's a real clear view.
Clear view. Also, another thing I wanted to say is, it seems to me that most of you are working by yourselves. Are most of you working by yourselves? Do people work in groups?
In terms of homework?
In terms of the homework. Try to work with other people. It's a good idea. I mean, I think it's probably good to try first on your own, but also talk with other people and bounce ideas off each other. It's sort of like well, like the weaknesses of one person may correspond to the strengths of another, basically, right? So you can help each other. Hybrid vigor. Okay. Does anybody want to say something about this? What can you? What will I say? Here I am, right, sitting at this point here, and I'm watching the blimp go by. Right? I see the blimp, and then I don't see the second blimp, but I see the third blimp, and I don't see the fourth and fifth, right? But what happens as time goes on? Right? when I see the blimp, the value is 1. When I don't see the blimp, the value is 0, right? Go ahead, Max.
Well, as you go to infinity, the interval on which it's anything other than 0 becomes infinitely small.
Yes.
And so when the limits just approach, like f equals 0.
But think of what happens. Think of what happens here. Is there ever a time where, from that point on, you never see the blimp again? Right? Because the sum of the harmonic series is infinite. Right? The sum of the harmonic series is infinite. Well, that means that the sum of the lengths of the blimps is infinite, right? So even though the blimps are shrinking in size, although you're going to see the blimps less frequently, you're going to still see it infinitely many more times, right? No matter if you sit there looking up, right, waiting, then you're going to see the blimp. No matter what point you look, no matter what time you start, you're going to see the blimp infinitely many times because the total length is infinite. Okay, so what does that tell you? Well, that the limit is not 0 and it's not 1 either, right? This limit actually doesn't exist. So limit doesn't exist. Okay, so this is a non-example, right? So the f sub n x do not converge pointwise to any function. Okay. Yes, Susan.
What does F4 look like? I just haven't seen it.
F4 would be the thing that starts here and goes on for a quarter. Right? So the length of that one would be 1/4. And it would start from 1/2 plus a third.
Oh, okay. So
Okay,
it's not-
and then 1/5 would start, the blimp number 5 would start here and go on for length of 1/5, and so on and so forth. Okay, I'll let you think about it. So yeah. Okay. Okay. Okay, let's any questions about that? Any questions about that? Yes, Arya.
So if it just kind of continues like where it left off,
Yeah.
then why?
But it wraps around. Remember, this is a video game, so it's like a video game. So once it reaches this end here, then it comes from the left-hand side.
Okay, so like if at 1/8 it like part of it was over.
Yeah, so maybe that this blimp goes partially here and partially here.
Okay.
Yeah. Yeah.
Why is the limit not 1 when you look up?
Well, what would that mean? That would mean that past some time, that would mean that there exists some n, such that past that n, you always see the blimp. Right? That's what that would mean. Well, that's not possible. Nor is it true that there's some n past which you never see the blimp. Okay? You're going to see the blimp infinitely many more times, but the frequency will decrease. Okay. So anyway, so that's a non-example. Don't worry too much about it. Think more about the actual example. Okay. Okay. So this is pointwise convergence, and there's some problems with pointwise convergence. Okay, mainly in the interaction with basic concepts of calculus. Okay, first is continuity. Here we have a bunch of continuous functions, and we take the pointwise limit of it, and we get something that's discontinuous. Okay, so continuity is not preserved under this sort of limit. Right? It may be that all the functions are continuous, but then the limit of the function, the pointwise limit of the function, is discontinuous. You also see that these guys are differentiable, and this is not differentiable. Okay, so so there's some trouble with that. I'm basically using the examples from your book. Another example of the bad interaction with differentiability is the following. If I let f sub n x be 1 over the square root of n times the sine of nx, then fn prime is going to be square root of n cosine nx. Okay, so now think about the limit of the f sub n's. If I take the limit of these f sub n's, what happens? What do I get? I get sine nx over the square root of n as n goes to infinity. Somebody other than Max? What happens? Yes, somebody said it.
It goes to 0.
Goes to 0, right? Because the sign is trapped between -1 and 1. You're dividing by a constant that becomes huge, right? So your function is going to be trapped between -1 over root n and +1 over root n, so it's squeezed down to 0. Okay, so the limit is 0. Okay, and if I take the derivative of that, well, I still get 0, right? The limit is 0. If I take the derivative of the limit, that's 0 also. Okay, but if I take, however, if I take the derivatives first, right? If I take the derivatives of my functions first, and then I take the limits next, right? If I take the derivatives first, I get this, and then I take the limits next. What happens then? Well, I really don't have any limit, right? It's not going to have any limit, right? The function is going to start oscillating faster and faster, and at the same time you're multiplying by a larger constant. Okay, so it becomes, as time goes on, it just becomes, the faster oscillation and larger values. Okay, so this function becomes really crazy. Right? No limit. Okay, so this doesn't even exist, right? So what does that tell you? That if you take the limit first and then differentiate, it's not the same thing as if you differentiate and then take the limit. These two things don't commute. Okay, so the interaction is bad. Okay. Okay, let me do a simple example related to integration. So if I take fn x to be the characteristic function of n plus 1. Okay, and maybe I haven't explained what the characteristic function is. So if I write something like this, chi, sub something, like chi sub e. Chi sub e would mean it's 1 if x is in e, and it's 0 if x is not in e. It's called the characteristic function of e, or the indicator function is another name used for it. Okay. I've also seen the notation big 1 sub e. for this kind of function. Chi, of course, is used for the characteristic. Right? But 1 makes sense because you've got this 1 here. It's 1 on E. Okay. So what is this function? Well, it's a function that on the interval n plus 1 takes the value 1, and it's 0 elsewhere. Okay. Well, what's the pointwise limit of this function? If I take the limit of this function as n goes to infinity, I fix some x, right? I fix some x. What's the limit of this function? Right? Fnx zero, right? It's going to be 0 because there's only going to be one time, or maybe 2, when the value is non-zero, right? Here I am sitting here out at 100 and a half, right? Well, when I reach f100, oh, I get a value of 1. But then after that, it becomes 0 again, right? Like, one good thing happened to you in your life, and the rest is kind of miserable. Okay. Okay. Yeah, that's how it sometimes feels. Okay. Just keep on waiting. The blimp will come. Maybe at decreasing intervals, but okay. 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 Right. So the limit of this thing is 0. Okay. But notice, like, if I take the integral, if I integrate these guys, right? What's the integral? What's the integral? The integral of this. The length is 1, the height is 1. Sorry. Yeah. The length is 1, the height is 1. Sorry, that must be confusing. The length is 1, the height is 1, the integral is 1. Right? And so if I take the limit of those, if I take the limit of the integrals, that's 1 also, right? But if I take the integral of the limit, well, that's the integral of the 0 function. That's 0. Right? So again, integration and limit don't commute. Integration and this kind of limit do not commute. Or another example, fn x, let that be n times the characteristic function of 0, 1 over n. Okay. So you take the interval, so it's 1, 0, 1 over n, and you take it at a height n times the n times your index. Okay. Okay. So this guy, what I've drawn here is f2, right? It has a domain of 0, 1/2, right? 0, 1 over n, and it has a height of n, right? Domain of 0, 1 over 2, and a height of 2 for f2. f3 would be 0, 1/3, go with height 3, and so on and so forth. Okay. Well, what's the integral of each of these guys? The integral over 0, 1 of each of these guys is going to be what? Too easy. How much area do I have here? 1, right? Right? And again, if I take the limit as n goes to infinity, that's a constant. So I get 1, right? And if I do it, but if I take the limit first, what do I get? What's the limit of these functions? If I take any point, right? I take some point here, what's going to happen? Well, at the beginning, I'm going to see something above me, and then after a while, it's gone, right? And never comes again, right? So, so the limit is 0. Right? The integral of the limit, same sort of thing happens. You get the integral of the 0 function. Sorry, you get 0. Okay. Okay, so these things don't really work well together. Okay. This limit and this kind of convergence and the normal basic ideas of calculus don't really interact too well. Okay. But all hope is not lost. There's another kind of convergence. So so different kind of convergence called uniform convergence. Okay. So pointwise convergence you can think of like this. F is the limit of f of n f of n converges to f pointwise on E means that for each x in E, the limit of fnx equals f of x. Right? For each x in E, the limit of fnx equals f of x. Okay. In terms of epsilon delta language, that means that for every epsilon greater than 0, there exists a time such that if you're past that time, then you know that the distance between fnx and f of x is smaller than epsilon. Right? Okay. We introduce another kind of convergence called uniform convergence. And this is really the whole reason why we're doing this chapter is to understand this kind of convergence called uniform convergence. We define it like this. If given any epsilon greater than 0, there exists an n such that if n is bigger than n, then the distance between fnx and f of x is smaller than epsilon for all x in E. Then we say Fn converges uniformly to F on E. So the setting is the same as before, right? Fn is a sequence of functions. This E lies in some metric space. Yeah, all right.
So I'm trying to see how this is different.
Yeah,
from
good.
pointwise, and
Yeah.
it seems like
Yes.
for pointwise we defined the x first, like we fixed the x.
Yes, exactly.
And then that epsilon and n condition was for that specific x.
Yes.
Whereas this, you can use the same epsilon and n for any x.
Well, okay. So the epsilon doesn't depend on the x, right? The epsilon can be any epsilon, right? So rather you think of this x, like given an epsilon, given an x, and given an epsilon, there's some n. Okay, so in terms of dependencies, maybe it's sort of clearer maybe it'd be clearer if every time I write that the dependencies, right? So this depends on epsilon, this n depends on epsilon, and it depends on x, right? Okay. Now this n, you see, doesn't depend on x. There's not even an x mentioned until later, right? So this n depends only on the epsilon and not on the x, right? So it's independent of x, right? It's uniform over the whole set. That's the name, right? Helen.
So, like, for pointwise convergence,
Yeah.
it's like you said, let x be an e, then for all epsilon is greater than 0, there exists an n.
Yeah.
And then for uniform, it's, I don't see how that's different. If you just let x be an e at the beginning of the pointwise convergence definition, it's the same as for all, because it's arbitrary.
So what this is saying is that if you fix a point, so means that if you fix any x here, then you take, no matter what epsilon you're given, there's an n that works for you. Okay. This is saying that given any epsilon, there's an n that works for everybody, for all of the x's. Okay, so math grammar is a little bit more precise than human vernacular grammar. Okay, so this is actually a completely different statement. So let me give you an example. So think about this thing here. So these guys, right, are going to converge to the 0. So this is the x to the n guys. Right? They're going to converge to 0, right? And if I take some point here, 1/2. Okay, I take some point here, 1/2, and I say, I'd like you to stay between, I want you to, you're saying that the limit is 0, well, I would like you to stay between this epsilon and that epsilon. And can you find me an n that works? You can find me an n that works for this point 1/2. Right? It looks like the third one, right? The third guy will work. Past the third guy, everybody works, right? Does the third guy work for this point here? Am I within?
Yeah.
Am I within epsilon of 0 for 9/10, say? No, right? Because the third guy is way up here, right?
Oh.
F sub 3 of 9/10 is up here. It's nowhere in the epsilon neighborhood, right? The epsilon, I give you an epsilon and a point, and you can give me an n that works for that point, but it doesn't work for every single point, right?
I see.
Right?
Okay. So the n that we're picking for uniform convergence works for every x and e.
Yes.
The one for pointwise convergence only works for that one x that we picked.
Yes, exactly.
Okay.
Yeah. So the n here depends on the point, and here is independent of the point. Okay. And the picture you want to keep in your head is that there's this tube. Okay. So you've got some function f. Okay. And you've got some epsilon. You've got some epsilon. So here's f plus epsilon, f minus epsilon. And what uniform convergence means is that if you fix this epsilon tube, then there's some n past which all the graphs lie in the tube. Okay, so uniform convergence means given epsilon, there exists a time such that if you're past that time, that all the f sub n, the distance between f sub n and x and f is smaller than epsilon for every value in your set, right? So every point has to lie in the epsilon, right? Every point satisfies that epsilon. That n works for every point with that epsilon, right? So everybody would have to be like, like this, past that point. Okay, so the picture you want to keep, the one you want to think, maybe a simple example of it would be f of x is 1 over n. Fn is 1 over n. Right? So here I've got, my first guy is 1, and my second guy is a half, my third guy is a third, my fourth guy is a fourth, a fifth, etc., etc. Right? They converge to 0. Right? They converge to 0, and if I say, I'd like you to stay within an epsilon of 0, well, you can find an n past which everybody is happy. Right? Right? All the functions, at every point, all the guys are going to be within that epsilon distance, will be within epsilon of 0. Okay? So here, it was impossible, right? It was impossible for epsilon less than 1 to do this, right? But here, it's definitely possible. Okay? So this is the tube. The tube is what you want to keep in mind, right, when you're thinking about uniform convergence. Given any tube, there's a time past which all the functions lie within the tube. Okay. 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 So remark. To say that a series converges uniformly means that the sequence of partial sums converges. Uniformly, as you might expect. Okay. Okay. So let's, in the remaining time, let's introduce one more useful theorem, the Cauchy criterion for uniform convergence. Okay. So again, same setting. Okay. So here it is. This converges uniformly on E. I should say I've seen sometimes this notation to mean uniform convergence, like a double arrow. Okay, I don't see it very often, but some people use this notation. F sub n converges uniformly on E if and only if, for all epsilon greater than 0, there exists an n such that if m and n are bigger than n, then fnx minus fmx is less than epsilon for all x in E.
Then it also converges pointwise.
Yes.
Okay.
Yes. It's, yes. Yeah, because convergent pointwise just means that you can find an n that works for that one point. While converging uniformly means you can find an n that works for every point, which it certainly implies that you can find an n that works for each individual point. Okay. Okay, so let's do the proof. If we have uniform convergence, then there exists an n such that this Cauchy condition holds for every x. Okay. Okay. So you say, okay, fix an x, fix an epsilon. Okay. We know that since Fn converges to F uniformly on E, we know that there exists n such that if you're past that time, then the distance of f of n x to f of x is smaller than epsilon over 2, right, for all x. So certainly if n and m are bigger than n, then the distance between f of n and f of m is going to be smaller than epsilon by the triangle inequality. Right? So then if m and n are bigger than capital N, certainly fnx minus fmx is smaller than epsilon by triangle inequality. So that's easy. The reverse direction is not much harder. Okay. So in the reverse direction, we know that in the reverse direction we know that this is true at each point. Okay. So we have a sequence of functions, and we have this fact. Okay, we have this fact. Well, that tells us that at each x, the sequence fnx is what? It's Cauchy, right? Did you say it? Yeah, it's Cauchy. So, by hypothesis, at each x, right? At each x in E, we know that fnx is Cauchy, so converges to something, right? Some value, call it f of x. So there is this thing that we're hoping is the limit. Okay. Like before that, we don't have this limit. Before we notice this, all we have is a sequence, right? But this actually does converge to some value. Call that value f of x. Okay. For each epsilon, we know that there exists n such that if n and m are bigger than n, then fnx minus fmx is smaller than epsilon over 2. All we're going to do now is just take the limit. Let m go to infinity. Okay. Let m go to infinity, and you get that from this inequality, you get that this thing is less than or equal to epsilon over 2, which is less than epsilon. Right? And this is for all x e, and this is for all x in e. Okay, so what does that tell you? That these guys converge uniformly. That's uniform convergence right there. mx.
At the top of that proof,
Yeah.
why in this case do we know that Cauchy implies convergence?
Because we're in C, which is complete. Yeah, our values, these are all complex numbers. Other questions? Okay, that's it for today.